Okay, moving right along, section 4.7. So now we're going back to a different type of differential equation called the Cauchy-Euler Equations. Sorry. And so a Cauchy-Euler equation has this form in general. It's an nth order differential equation. But the coefficients are not constants anymore, right? So notice that you're multiplying each nth order derivative by x to the n, right? So that creates a differential equation. As a special case, let's look at the second order ax squared y double prime plus bx y prime plus c equals g of x. So if it's a homogeneous equation, we'll just get equals 0. If g of x is something else, well, now you either have undetermined coefficients or variation of parameters to be able to find the particular solutions. Okay, so I already have one example up here. Let's see, I'm not sure this is going to work right. Bear with me, I'm still getting used to this, as you can see in the last video, apparently. All right, so yes, so as a special case, we're concentrating on second order equations. So the idea, what works here is to try solutions of the form x to the m for some number m, right? As a first example, we'll use, so we're switching to x as our dependent variable here. So x double prime equals 2 over t times x prime. And first thing you should do, of course, is notice that there's no x here, and you can rewrite it in its standard form, t squared x double prime minus 2t x prime equals 0, right? And so again, we're just going to guess x is equal to t to the power m. So what would m be? Well, when you take the first derivative, x prime, you get m t to the m minus 1. And when you take the second derivative, you get m times m minus 1 t to the m minus 2. Right? So when you plug those in, you get this as your auxiliary equation. Right? So the t squared times x double prime, when you multiply t squared times t to the m minus 2, you just get t to the m, right? And so all of this is multiplied by t to the m. But when we divide out, we get m squared minus 3m equals 0. I hope that's clear, which has two solutions, 0 and 3. So now we just form our linear combinations, right? Y equals c1, well, t to the 0 plus c2, t to the 3. So, yep, you're right, c1, t to the 0 plus c2, t to the 3. But t to the 0 is 1, so that's why it's just c1. Okay, so that's the idea of Cauchy-Euler equations. The main thing to remember is that you're looking at, you're guessing the solution x to the m here, rather than, say, e to the x or e to the mx or something else. So let's look at another example while we're at it. So example 2. So I think I'll take this from the book as well. This is going to be number 6, just as in the last section. So 4.7, number 6. We want to solve the following equation. This is going to be x squared times y double prime plus 5x y prime plus 3y equals 0. So it's a homogeneous equation. And we'll do those for the time being. All right, so now we want to solve this equation. So because we recognize it as a Cauchy-Euler, you have the same exponent as the order of the derivative. So x squared and second derivative, x to the 1, first derivative, and of course this is x to the 0, and the 0th derivative is just y. So let's guess y equals x to the m. And, well, we have, well, I'll write them down again. So y prime, of course, is m times x to the m minus 1, and y double prime is m times m minus 1, x to the m minus 2. So when you plug all that in here, you get x squared times m minus 1. Sorry about that. Let's fix that. Okay, that's only slightly better. Okay. M times m minus 1 times x to the m minus 2 plus 5 times x times y prime, which is m x to the m minus 1, plus 3 times y, which is 3x to the m equals 0. So x squared times x to the m minus 2, of course, is just x to the m. And then we have m times m minus 1 plus 5m plus 3. And I just factored out the x to the m, right? And so you can divide by x to the m. We're assuming x is, well, not 0 here. And so when you multiply this out, you get a quadratic equation. M squared minus m plus 5m is plus 4m plus 3 equals 0. And that you can factor m plus 1, m plus 3 equals 0. And so that gives us two solutions, -1 and -3. Right? So be careful. This was not a regular linear equation. So we don't get e to the negative x, e to the negative 3x. This was Cauchy-Euler. We're looking at x to the m. So if m is -1, our first solution, our y1, if you will, is just x to the -1, and y2 is just x to the -3, and you can check these are linearly independent. And so our complete solution, or general solution, y of x, is just going to be c1 x to the -1 plus, c2 x to the -3, and that's good enough. Okay, so that's how these Cauchy-Euler equations work, specifically. So maybe wondering if I can do one more example here. All right, let's try it. Oh, I might run out of space here. All right, hang on. Give me 1 second. All right, so example 3. At least for this video. So here we want to solve x cubed, y triple prime, minus 3x squared, y double prime, plus 7x y prime, minus 8y equals 0. Right. So again, we're just going to guess as our solution y equals x to the m. So notice we're going to need a third derivative here. If I can do that way up here, our third derivative will be m times m minus 1 times m minus 2 times x to the m minus 3 now. So when you plug all that in here, you're going to get x cubed times all this, m minus 1, m minus 2, times x to the m minus 3, and then minus 3x squared times y double prime, so we get the m minus 1, x to the m minus 2, plus 7x times mx to the m minus 1, minus 8y, which is just minus 8x to the m equals 0. So, right, you pull out the x to the m, and you're going to get, well, m cubed something here. So m cubed and then minus 3m squared. Right, minus 3m squared, and then plus 2m. Right, and then minus 3m squared plus 3m and then plus 7m minus 8 equals 0. Yep, divide by the x to the m. And so we get a cubic equation, m cubed minus 6m squared. Right, I'm combining these two terms. And then 2m plus 3m is 5m. 5m plus 7m is 12m plus 12m minus 8. So once again, we're solving a cubic equation here, not just a quadratic equation. So how do you do that? Well, you can just use your calculator. It turns out that this is a perfect cube. This is just m minus 2 all to the power 3 equals 0. So there is only one unique solution here, m equals 2, right, with multiplicity 3. So this is interesting, right? So what you end up with is, I can go back to this here. Hang on. Oh, bear with me. All right, so you're going to end up with y equals x squared. But obviously, you can't have c1x squared plus c2x squared plus c3x squared. They're not linearly independent. So what do you do when you have multiplicity more than 1? Well, the answer is, amazingly enough, is, Right, so this is our y1 of x is x squared. Your second linearly independent solution is to multiply the x squared by a logarithm, log of x. Okay, so that gives you a second linearly independent solution. And, well, we need a third one. So what do we do now? Multiply by another log x. So this is going to be log of x, the whole thing squared. Remember, this is not the log of x squared. You can't take the 2 in front here. So that means our general solution, well, I didn't mean C for complementary. Obviously, this is a homogeneous solution, a homogeneous equation, rather, that equals 0. So we don't need yc here. So the general solution is just going to be y of x equals c1x squared plus c2 x squared log x plus c3 x squared log of x, the whole thing, log of x squared. And that gives you your solution. So that's what happens when you have repeated roots. You just multiply by log of x. If it was a double root, right, multiplicity 2, you just multiply by log x. Since this is multiplicity 3, we have to multiply by log x squared to get the third linearly independent solution. Right. So that's sort of what can go wrong when you have repeated roots here. So I think that should do it, at least for Cauchy-Euler equations. Again, the basic idea is to look at solutions, y equals x to some power. We're using m. Other books use different letters, but I'll stick to this book. And then don't forget, when you end up with a repeated solution to the auxiliary equation, you multiply by log x to get the independent solutions there. So I hope that helps for Cauchy-Euler Equations, section 4.7.